We talked about chemical reactions a lot, but we left out one important component of chemical reactions, which is energy. Energy can be a product in chemical reactions or it can be a reactant. For example, in this match head reaction, the reaction that occurs when you light up a match, it's basically oxidation of phosphorus. It releases energy. So energy is a product in this chemical reaction. And study about energy component in chemical reactions is what we are going to learn in this thermochemistry chapter. So what is energy? Energy is the ability to do work or to transfer heat. Think about a pitcher. He can make the ball move. He can use his energy to make the ball move. That is basically doing work on the ball. So energy can do work. If you have energy, you can do work. What about a propane gas? What can it do? The energy from a propane gas can be used to heat up some water or heat up some food. So you can either do work if you have energy, or you can heat up something if you have energy. So we can say energy is the ability to do work or to transfer heat. You may already be familiar with first law of thermodynamics, which says energy cannot be destroyed or created. It can only be converted to from one form to another form. A classic example of that is what's going on in a hydroelectric power station. Let's consider this. So you have water stored at a height. So water contains higher potential energy when it is on a height, because the potential energy of an object that is at a certain height can be height from the ground can be calculated using this formula: mass times acceleration due to gravity times the height of the object from the ground. So that's going to give you the potential energy of the object relative to the ground. Objects that are elevated contain higher potential energy. Now, as the water moves down, flows down, it contains kinetic energy. Kinetic energy is basically the energy due to motion. So as water moves with a certain velocity, it obtains kinetic energy. The formula for kinetic energy is half mass of the object times the velocity squared of the object. Now this kinetic energy, the fast moving water, is used to rotate the turbines. Okay, so rotating turbines is equivalent to doing some work. So you have extracted mechanical energy out of the kinetic energy when the water moves the turbines. And finally, the turbines, since they are connected to magnetic shafts, rotating magnetic field creates electric field. So that's how you have converted mechanical energy to electrical energy in a power station. Okay, so energy is not wasted. The energy at any point of this process is constant. The potential energy of water here and the potential energy plus kinetic energy of water here are the same. Energy is neither created nor destroyed. Now, you can also get electricity from coal. How? So coal can undergo combustion, and the combustion reactions produce energy. And this energy could be in the form of heat, which is you can use that energy to heat water. And water will convert to steam. And the steam is compressed. It's going to be condensed or compressed. And then it is used to rotate turbines again. Compressed air can do mechanical work. So you rotate the turbines, and the turbines that are connected to magnetic shafts will produce electricity. So it's connected to a generator which produces electricity. So we want to focus on reactions. Where does this energy come in a reaction? How do reactions release energy? So basically, each chemical substance contains some amount of chemical energy. So carbon contains some amount of chemical energy, oxygen has some energy, and carbon dioxide contains some energy. Turns out the energy content of carbon plus oxygen is higher than the energy of CO2. So when carbon plus oxygen react to produce CO2, the excess energy, since CO2 has less energy, carbon plus oxygen has to get rid of some energy. The excess energy will come out in the form of either heat or work. Okay, so that's how this energy excess is released. This is released because products have lower energy than reactants. We are going to talk about units. So if you want to get the SI unit of energy, you have to plug in SI units in the formula. So let me pick the kinetic energy formula and substitute SI units. The SI unit for mass is kilograms. Velocity is distance over time. So the velocity's SI unit will be distance, which is meters over second. And velocity should be squared. That means these units should be squared. So the units that I get out are kilogram, meter square over second square. Kilogram, meter square per second square. Per second square can also be written as seconds inverse square. Well, this is the SI unit of energy, and it's also called a joule. So 1 kilogram meter per second square, sorry, meter square per second square, there should be a square here, is also equal to 1 joule. Now, there are also other units such as calories and British thermal units. A calorie is slightly bigger than, not slightly, actually four times bigger than a joule. A calorie is 4.184 joules. Now, this calorie with a bigger C, that's a nutritional calorie. You find it on the back of a cereal box, nutritional calorie. This is nothing but a kilocalorie. In other words, 1,000 of these, 1,000 calories. British thermal unit, this is the bigger SI unit. It is equal to 252 calories. In other words, 252 times, since each calorie is 4.184 joules, we can say a British thermal unit is 252 times 4.184 joules. All right, now let's talk about where this energy of a substance coming from. What constitutes to the energy within a substance? So each substance has different amount of energy. Carbon has certain amount of energy. Carbon monoxide has certain amount of energy. CO2 has different amount of energy. O2 has different amount of energy. You know that different fuels have different amount of energies. So what is the energy within a substance due to? Well, it's due to the bonds and also due to the motions of the molecules. So different substances have different arrangements of atoms, which will lead to different potential energy within the substance. So this potential energy this time is no longer because of the height at which the molecule is from the ground. It's because of the attractions between the charges within a substance. So you have, let's say, carbon is bonded to oxygen. So there is a nucleus of the carbon and you have electrons around it, and there is nucleus within oxygen, there are electrons around it. So there is different kinds of attractions and repulsions going on. So the electrons from the carbon get attracted to the oxygen's nucleus. Electrons from oxygen are attracted to the nucleus of carbon. There are minimal repulsions also between the electrons, and there are also repulsions between the nuclei. So there are all sorts of interactions between charges. And to calculate the potential energy between two charges, you can use the Coulomb's law. So the electrostatic potential energy between any two charges is given by the Coulomb's constant times the charges Q1 and Q2 divided by the distance of separation. And since different substances have different bond distances, since the arrangement of atoms is different in different substances have different potential energies. Now, there is also kinetic energy within a substance. There is translational motion. So molecules can go from one position to another. That's called translational motion. The bonds themselves can also move. The bonds can contract and they can expand. This is called vibrational motion. They can also bend and twist. There are also molecules can rotate around an axis. So all these motions together constitute the kinetic energy within a substance. Okay. And how do we measure the kinetic energy? Well, using temperature. There is a direct relationship between temperature, the Kelvin temperature, and the average kinetic energy within a substance. So if you increase the temperature, molecules are going to move even faster, and the average kinetic energy of the molecules in the substance will goes up. So remember, temperature is the measure of average kinetic energy within a substance. Now, the sum of all the potential and all the kinetic energy within a substance is what constitutes the chemical energy of a substance. And we're going to call it internal energy and represented by the uppercase U or E. So, what's internal energy? It's the energy due to all potential and all kinetic energy within a substance. It's everything, every energy, possible energy within a substance. Okay. So, internal energy is the sum of all potential and kinetic energy within a substance. And different substances have different amounts of internal energies or chemical energies. Now, you cannot measure the internal energy of a substance because you don't have information about all possible kinetic energies. You don't have information about every little motion. You don't have information about um, all the electrostatic potential energies because there are lots of electrons and protons, and there are also other subatomic particles. So you can't get a number, you can't get a value for the internal energy. It's something that you cannot measure precisely. Okay. What you can do, you can only talk about the relative energies of two different substances. For example, you can say, okay, compared to oxygen atom, oxygen molecule has lower energy than oxygen atom. You can only talk about their relative um, um, internal energies. But what you can measure is the change in internal energy. Change is represented by this delta sign, okay? So delta U or delta E, the changes in internal energy of a substance, can be measured. When a substance goes from one value of internal energy to another value of internal energy, its change can be measured. And we are going to see how to measure this change, okay? So here you have a gas enclosed in a cylinder. It could be methane gas or oxygen or any gas. Now, how does this gas lose its internal energy or gain its internal energy? By the way, whatever you're observing, that will be your system. We always refer to the part of the universe that we are investigating. So, suppose you're looking at how the internal energy of this gas changes, then the gas will be your system. Everything else we call it surrounding. So, here the piston that is fitted here, the container, all these form your surroundings. And the system plus surroundings together, we call it the universe. So you can say universe is system plus surroundings. All right, now back to our main question. How does this gas change its internal energy? Well, it can give it off in the form of heat. Heat is nothing but thermal energy. So how do you know that it has given off its internal energy in the form of heat? Well, its temperature will change. Heat is a form of energy that causes the object's temperature to change. It can also be used to break bonds. So if you see a change in temperature of this gas, then you can conclude that the internal energy has gone down and it has been released in the form of heat. So you can say the energy is released in the form of heat. Okay. Now we have to use a sign convention here. Q is how you denote heat. You never say heat of the gas. Heat is always the output or the input. It is referring to the amount of energy that's coming out or going in. And it's always associated with a temperature change. So if you see, if it is heat coming out, if the system is losing heat, if the system is losing heat, then Q is negative. Q is negative because losing heat causes the internal energy of the system to drop. So Q will be negative in that case. And if system is absorbing heat, if the system is absorbing heat, then the Q of the system is positive. Because if a system absorbs heat, its internal energy will increase. So hotter gas is more energetic than cooler gas. So let's talk about this heat a little bit more. Remember, heat and temperature, they're totally different things. Heat is a form of energy, but temperature is a measure of the thermal energy or the average kinetic energy of particles in a substance. Okay, they both have different units. Temperature's units are Celsius, Fahrenheit, or Kelvin. The units of heat will be something like joules or kilojoules or calories. They are two different things. Temperature is a measure of heat, but temperature is not the same as heat. Okay, now we said heat is energy that causes temperature to increase or decrease. So if heat always flows from hot object to cold object. So if you have hot object here, there are more agitations in the molecule. So this contains a lot more internal energy than a colder substance. And heat always flows from the hot object to the cold object. Heat is represented by Q. And we said heat gained by the system is positive. So if Q is gained by the system, we say Q will be positive here for this system. And Q is lost by the system. So Q will be negative here for the system on the left-hand side. Okay. All right. Now, how do we calculate the Q? Is there a formula to calculate Q? Yes, there is. Now, heat can be measured using this formula. Q, which is heat lost or gained by a substance, that's equal to mass of the substance, so M there stands for mass, times the specific heat of the substance, so this is the specific heat, times the change in temperature of the substance, okay, times the change in temperature of that substance. So what is C? C, the specific heat, is defined as heat needed per gram of substance to raise the temperature of that substance by 1 degree Celsius. That's what specific heat means. For example, specific heat of water is 1 calorie. So specific heat of water is, it's a standard number because every substance has different specific heat. For water, it is 1 calorie. Think about it. What should be the unit? It's heat per gram. So it's going to be 1 calorie per gram. And for 1 degree Celsius change, so per degree Celsius change, okay, this is what the unit of specific heat is going to be. Unit of energy over unit of mass times specific temperature change. So water needs 1 gram of water needs 1 calorie of energy to change its temperature by 1 degree Celsius. Okay, so suppose you want to heat water from 25 to 26 degrees Celsius. That's a 1 degree Celsius change. It would take 1 calorie of energy per gram of water. Okay, so suppose you have 10 grams of water. Suppose you have 10 grams of water. And suppose you want to take it from 25 degrees Celsius to 35 degrees Celsius. What do? What's the temperature change here? Temperature change is always measured as final minus initial. Any change, delta is representing change. Change is always final minus initial. And here it's 35 minus 25, which is 5 degrees Celsius. So you want to raise the temperature of 10 grams of water by 5 degrees Celsius. Think about how much energy it would take. Every gram takes a cal, so 10 grams should take 10 times 1. So you have to multiply, so you have to get the specific heat and multiply it by the mass of the substance, which is 10 grams, right? And that would give you the amount of energy for 10 grams, okay? So it's going to give you the amount of energy for 10 grams for 1 degree Celsius change, okay, per degree Celsius change. Since you want to change the temperature by 5 degrees Celsius, all you need to do is multiply it by 5 because you want to change it by 5. That means you need 5 times more energy. That's why you're multiplying by 5. Look at what I calculated. I calculated the energy for 10 grams to raise the temperature by 5 degrees Celsius. What I calculated is basically the total energy needed. And as you can see how we got the formula, we are multiplying the specific heat by the mass times the temperature change that you want. Okay, so Q is equal to mc delta T. The units for specific heat are always units of energy over units of mass times temperature change. Okay, you never want to write just joules as the unit for specific heat. Specific heat is per gram per degree Celsius. So make sure you have the correct units. And when you multiply it by unit of mass and temperatures units, that's how you end up with joules as the unit for heat in this expression. Okay, specific heat is a specific property of a substance. It's a property of a substance. So different substances and different materials have different specific heats. For example, as you can see here in this list, metals, iron, copper, lead, these are metals. Metals have very low specific heats, and other substances like air, uh, ice, and liquid water, you can see they have very high specific heats. Water has very high specific heat. Think about what that means when substances have low versus high specific heats. Let's say you put a metal spoon and wooden spoon in a pot of soup. You can, by experience, you know that the metal spoon gets hot quicker. Why is that? Because it has low specific heat. Metals have low specific heat. That means they change their temperature very quickly. So for every 1 degree Celsius change, okay, per gram, I need only zero point 0.4 joules of energy. So as the wooden spoon takes 1.74, it takes a lot more energy per gram to raise its temperature by 1 degree Celsius. So as the same amount of energy is supplied, this one is going to increase its temperature quickly than the one that has higher specific heat. So coming to water, water has very high specific heat. We said it is 1 calorie per gram degree Celsius, which is the same as 1.484 joules per gram degree Celsius. So this here, the unit is in joules per gram degree Celsius, okay? Water has high specific heat. That's how water regulates the climate. It can absorb a lot of heat. For every degree Celsius, it absorbs a lot more. 4.18 joules is a lot. Compare that with the metals. Metals take only less amount of heat, whereas water can take large amounts of heat to change its temperature by 1 degree Celsius. It's very temperature resistant. It resists temperature change. So oceans can basically absorb a lot of heat in the summer without changing their temperature. And in the winter, oceans will release a lot of heat without changing their temperature very much. So water, as you can see, it's going to resist temperature change. So bringing this system of gas up again, we said it can change its internal energy by gaining or losing heat. Another way it can change its internal energy is in the form of work. Okay, suppose I push the piston down. Okay, suppose you have a gas and I push the piston down now. Okay, so we went from here to here. What happens to the gas? The gas gets compressed, and compressed gas has a lot more internal energy than uncompressed gas. So you can change the internal energy by just forcing the piston down. And forcing the piston down is the same as you doing work on the gas. Okay? Now, another way you can change the internal energy is pulling the piston up. In that case, the gas expands. So as the gas expands, the gas is lifting the piston. So in this case, the gas is doing work and it's going to lose its internal energy. Okay, so the key point is you can also make the system do work or do work on the system to change the internal energy. So what is work? Work is nothing but mechanical energy. And work is said to be done when a force causes an object to move by a certain distance. Okay, so you suppose you have a ball and you're moving it by a certain distance. You're applying a force on it, let's say F, and let's say you moved it by a certain distance. Okay, let's call it dx or d. Okay, now force times the distance by which the object moved will give you the work done on the system. Now, when gases are expanding, we have to change the formula slightly. Okay, so here, let's say this gas is expanding. So this time the gases are moving up by a distance d. So here d is nothing but the height of the height by which the piston got displaced. So notice what happens to this formula if we multiply by area and divide by area on both sides, okay, on the right hand side. So multiplying by area and dividing by area doesn't do anything to this, but we arrive at a new formula. Force over area is nothing but pressure, okay? So this is giving you the force acting on the piston divided by the area of the piston. It's going to give you the pressure, and it's external pressure, the pressure on the piston. So this is going to give you external pressure. And think about what does area times the distance by which the piston has moved will give you. It will give you the change in volume. It's going to give you this part of the volume, right? This is the change in distance, change in by which the piston has moved up, times the area of the piston is going to give you the volume change of the gas. Okay, so that part is the volume change of the gas. So work is pressure, external pressure times the volume change. That's going to give you the work done by that gas or the work done on the gas when the gas expands or contracts. We need a negative sign because the sign convention is always work done by the system is negative. Okay, if you do work, if you are doing work, you lose energy. Okay, if work is done by the system will lose energy, so it should have a negative sign. So work should be negative there. On the other hand, if work is done on the system, if you're compressing the gas, if you are pushing the piston down and doing work on the system, gas gets compressed, its internal energy increases. So since it's an increase, work done on the system is always positive. We represent that with a positive sign. That's how you know whether it's work done on the system or by the system, okay? Now think about it. If we don't have this negative sign, then you cannot get this convention. So we put that in there so that we get this correct sign. When gases expand, work is done by the gas, so you should get a negative sign. Here, the volume change is positive because as the gas expands, the final volume is higher than the initial volume. So delta V is going to be positive, but because of this negative sign, work will end up negative when the work is done by the gas, okay? And you will get a positive sign for work when work is done by on the gas. So when work is done on, volume change, the final volume is less than the initial volume. So delta V is going to be negative, and negative of negative will give you a positive sign for work when work is done on the system, which is what we want. Okay. So here's the formula to calculate work. It's negative of external pressure times the volume change in the gas. Okay, volume change for the gas. So internal energy, we said, can be changed either in the form of heat or in the form of work. So according to first law of thermodynamics, since energy has to be conserved, the amount of heat lost or gained and the amount of mechanical energy lost or gained by the substance, those two should add up to give you the internal energy change of the substance. So for example, let's say this substance had a final initial internal energy, some amount of initial internal energy. We don't know a number for it because we cannot measure it, okay? So let's say the system has lost 20 joules of heat. So your Q is 20, negative 20 joules. Let's say the system has been compressed, okay? So if it is compressed, it's gaining internal energy in the form of work. So work done on the system, let's say it's equal to plus 60 joules of energy. Okay, so in that case, what will be the so in that case, due to these differences, it has reached some final energy. So what is the difference in the final and internal energy? Well, 20 joules have been lost, but 60 joules have been gained. So totally there is a gain of 40 joules, right? So the difference in energy here, so the delta E, which is the final minus initial, that's equal to the sum of these two, because energy cannot go anywhere if it has been lost this way and it has been gained this way. So the change here should reflect that. So that we can say delta E is equal to Q plus W. So this is the first law of thermodynamics. Remember, we can represent the change in internal energy by either delta U or delta E. It's the same thing. And change will be always equal to Q plus W. This is from the energy conservation. And we know how to calculate Q. So if you see a temperature change here, you can calculate it, okay? If you don't know this value, record the temperature change and calculate Q because you know the formula for Q, which is mc delta T. You also know the formula for work. If you know the external pressure and the volume change, you will be able to calculate the work as well. It's negative P delta V. So that's by calculating the work and the heat, we will be able to gauge the difference in energy, difference in the internal energy of the gas when it loses or gains heat or mechanical energy. Now, what does delta E or change in internal energy mean for a reaction? For example, here you have combustion of octane, which is nothing but gasoline the fuel that you use to drive cars. So when you look up a chemistry textbook, usually the reaction is written out with delta E, change in internal energy, or you will also see something like delta H, which is called change in enthalpy. And I'm going to talk about this just in a bit. What are these? So delta E, the change, you can if you want, you can call it delta E reaction if you want. You can put a delta E sub reaction. It is basically the change in energy between the products and the reactants. Delta is always final minus initial. So the final here means our products. So it's the change in energy between, you can say, products energy minus the reactants energy. Okay, and as you can see here, your octane and oxygen, they carry higher internal energy than your products. Okay, so since the products have lesser energy, delta E here is going to be negative. So delta E is negative in this case. Delta E is negative. And what does negative delta E mean? It means energy is released. So think about it. How does high energy reactants go to low energy products? They have to get rid of their energy. So this is an exothermic reaction. You know that combustion reactions produce a lot of heat. So we can say for exothermic reaction, okay? In other words, energy is produced, energy is released or produced. For these reactions, delta E is negative, okay? You have a negative change in internal energy between from reactants to products. You can also write the opposite. Suppose you have a reaction. Suppose I'm going to write it here. Suppose the delta E is positive. That means your products are going to be at a higher energy. So reactants have low energy, products have high energy, and reactants have to absorb energy to make high energy products. Okay, so delta E is positive means endothermic reaction. Endothermic reaction. And what that means is energy is absorbed by your reactants. Okay, energy should be absorbed by the reactants to carry on for them to convert to products. Okay, all right. So this, I'm going to label it here on this chart. So this difference in energy between the products and reactants. So this difference is my delta E, the difference between products and reactants. Okay. All right. So let's carry this reaction. Suppose we carry this reaction in a car. What, how, how does this delta E, what does this delta E convert into? Suppose you burn, how are you going to release this excess energy, the delta E? Suppose you burn this octane in a combustion engine. So the difference between the energy and products is it's going to be released in two forms. One is in the form of heat. So some of the energy is going to be some of this internal energy difference. It's going to be converted into heat, which is I'm calling it Q. But most of it is converted into work. Okay, most of it is converted into work. Think about it. In a car's combustion engine, what's really going on is you basically you compress a mixture of air and your fuel. Your octane and oxygen mixture are compressed. So you have a piston here. So the internal combustion engine has air and basically the reactants, air and octane, which are compressed under high pressure. Now there is a spark plug which ignites this mixture. As soon as it ignites, these reactants rapidly convert into carbon dioxide and water vapor, which are, this is lots of gas. You're forming a lot of moles of gas. So the mixture is going to rapidly expand. Okay, so once you ignite it, the products are formed. And now the mixture, since you have a lot of gases formed, so those are going to push the piston up. Okay, so those are going to push the piston up. So now your reactants, your gases here, okay, your reactants or products, they have performed work. Work is done by the system. That means the work is negative. Okay, so as you can see, work is negative. That means internal energy is lost in the form of work. Some of this internal energy is lost in the form of work. It is used to keep your car running. So this work, it can be transmitted to the wheels of your car and that's how you make the car move. You extracted this internal energy mostly in the form of work, but some of it is going to be lost in the form of heat. Now, what if you carried out this reaction in a constant volume container? Okay, so this is let me go ahead and write it. This is a constant volume here. What we're having is a constant volume container. So we call it a bomb. This container is called a bomb. I'll tell you just in a bit why it's called a bomb. It's basically a very sturdy metal can with very thick walls, and the top is sealed off, and you can let air into it. So if you want to, you can put your octane gas inside this bomb, inside this container. There will be a valve to let oxygen inside, and there is a spark plug to ignite this mixture. So this is a constant volume because the gases, as they're formed, cannot escape out. They cannot push. Like in here, they push the piston up, so they're going to perform some work. But here, they cannot expand. That's why we call it a constant volume, okay? It is sealed off. So think about the work. Do those gases do any work here? So work here, since it's constant volume, there is no change in volume for the gases. So delta V is 0. Work is negative P delta V, and delta V is 0. That means work is 0. Those gases don't do any work, like in this case where they're expanding and pushing the piston. Okay, so if work is 0, you can apply the equation delta E is equal to Q plus W. So delta, since work is 0, since this portion is basically 0, your delta E is equal to Q. That means this delta E, whatever this difference between the products and reactants is, all of it is converted to just heat. So all of it is just converted to heat if you carry out this reaction under a constant volume. So this portion, delta E, is equal to all Q, only Q. Okay, so I can write, so remember this, what we're trying to say is if you have Q, if you perform the reaction at constant volume and measure the heat, this is basically delta E. This is a very important equation I want you to remember, okay? So, so what is delta E for the reaction? It's basically nothing but the difference in energy between reactants and products, which can be measured as the heat released by the system, okay, as the heat transferred by the system at constant volume. That's what delta E is, very key. So let me make a note here again. Delta E is Q at constant volume. Now, what if we carry out this reaction under constant pressure? So let's switch to constant pressure. What does that mean? Well, you can just burn it in a drum, okay? When you burn fuel or when you burn, like, say, wood outside, if you want to keep yourself warm, you burn wood. You don't put it in a constant volume system. You just let the gases expand out, whatever gases are formed. You just let them expand out and reach whatever the atmospheric pressure is. So the gases are allowed to expand out and reach a constant atmospheric pressure, okay? So in this case, yes, we have some work because the gases are pushing the atmosphere. We do have some work, but it's very less. The work is negligible in this case. Okay, because what are the gases doing? They are just pushing the atmosphere. That's negligible, and we don't know even how to calculate this work, okay, because here you can record the volume change, but when the gases are pushing the atmosphere, we don't know how to measure this work, but we know that it's a very tiny value. And the rest of the energy comes out in the form of heat. So the rest of it comes out in the form of heat. So this is Q at constant pressure. Now, most of the time in the lab or when you perform reactions in real life, you're under a constant pressure condition. And the work involved is very negligible. We don't even know how to measure it because the atmosphere is pushed out, atmosphere is too big. So that's negligible and you can ignore it, and you don't, because you don't know how to calculate it. So the amount of energy released at constant pressure, the amount of heat released at constant pressure is what is important, okay? And this portion, this is called enthalpy change. This is your enthalpy change of the reaction. So enthalpy change is nothing but heat or absorbed or released by the reaction at constant pressure, which is more useful because most of the time you do reactions at constant pressure, not constant volume. Okay? So I want you to understand this difference here. Delta E refers to the change in energy between the products and reactants. It's basically equal to Q. It's equal to the heat released or absorbed at constant volume. Whereas delta H and delta E, they are almost equal, but delta H refers to the heat released or absorbed by the system at constant pressure. Okay? You can look up the value for delta H in any standard thermochemical data. Turns out for combustion of 1 mole of octane, the delta H of the reaction will be around 5,500 kilojoules per mole, and its negative value suggesting that this is an exothermic reaction. Okay, there is something else I want to point out. I want to talk about something called a state function. State function is a property that depends only on the initial and final states of the system and not how the system got there. That means it doesn't depend on the path that it took. One example is altitude. For example, let's say you are climbing a mountain. Okay, think about altitude versus the distance traveled. Distance traveled. Okay. So suppose you are here, you have a certain altitude. Suppose you are here, you have certain altitude. Suppose you have here, you have certain altitude. Okay, it doesn't depend on the path that you took to get there, right? So altitude doesn't depend on the path that you took. So this is It doesn't depend on how you got there. Once you are there, you have a certain value for altitude. So this is a state function. So you can say altitude is a state function. Now, distance, think about it. Is it a state function? Well, does distance depend or does it not depend on the path? So if you took a very windy road to get here, you would have traveled a lot of distance. Let's say you climb the mountain, you're a great climber, you climb the mountain, then your distance is shorter. So it depends on how you got there, right? The distance traveled depends on the path, and that's why this is not a state function. This is not a state function. Let me reiterate, state functions they do not depend on the path. Okay. So just like altitude here, your energy of a substance, it doesn't depend on the path. Once you have octane under a certain condition, let's say you have 1 gallon of octane at 25 degrees Celsius, it has a certain amount of energy. It does not depend on how you made that octane, whether you got it by cooling the gas or whether you got by heating it, it doesn't matter. Likewise for, let's say, water. So let's say you have 1 gallon of water at 25 degrees Celsius. You could have made it by melting ice. You could have made it by condensation of water vapor. It doesn't matter. Once the substance is at a given state, it carries a certain amount of internal energy. Okay, so internal energy is a state function. Internal energy, we can say internal energy is a state function. And likewise, enthalpy is also going to be a state function is a state. These are state functions. Once a substance is under a certain temperature, pressure, certain amount, once it is at that state, it has a certain amount of internal energy. It doesn't depend on how you made it. Okay. So the difference, so if you have a state function, the difference delta E also doesn't depend on how you carried the process. So let's say here you carried the process in 3 different ways. Okay, so it doesn't matter every time. The delta E is just final minus initial. Delta E is the same. Energy of the products minus energy of the reactants. It's the same amount of change in internal energy between reactants and products every single time. It doesn't matter how you converted those products to reactants, whether you converted them in an internal combustion engine or in a bomb, which is basically a constant volume um, container, or if you just burnt it under constant pressure, it doesn't matter. So E is a state function. So delta for state functions, change is always final minus initial. Doesn't depend on the path. You get the same amount of change every single time, regardless of how you carry out the reaction. Whereas if you look at Q and W, they depend on how you carried the reaction. If you carried out this reaction in a combustion engine, you derived a lot of work out of it. If you just burnt it, or if you just burnt it in a constant um, uh, volume, you did not get very much work. Here, actually, the work is zero. Most of it is converted into heat in these cases. Okay, so Q and W depend on the path, depend on how you carried the reaction, whether at constant pressure or volume. So we can say Q, the heat and work are not state functions. They are path functions. These are not state functions. Okay, so make that distinction there. As engineers, you're always trying to carry out the reaction in such a way that work is maximized and heat is minimized. Okay, chemists are interested in carrying the reaction so that heat is maximized because the heat gives you a good estimate of the difference in energy between the reactants and products, and that's what chemists are interested in, how much a substance's internal energy relative to another substance's internal energy. Okay, and you must also know as an engineer that you can never get just work. You can always get only heat. Delta E can be converted totally to heat, but you can never get only work from that difference in energy between the products and reactants. Some of the energy is always lost as heat. You can never get 100% work. Okay, a good engineer would always try to maximize the efficiency or maximize the amount of work that is extracted out of a reaction. Okay, hope this helps. I'm going to do one sample problem and then we are going to apply all these concepts to a lot of other different things. But here's the core of this chapter. What is heat? What is work? What is internal energy and the difference in internal energy between products and reactants, and also what is enthalpy change. So that's the basics that I covered in this video. Let me know if you have questions.